Now we're going to consider the force between a smoothly charged rod, kind of like our Teflon rod, and a point charge. Smoothly charged rod has total charge Q, and it sits on the x-axis. So we could have it come along here, and the point charge is along its length, so it also sits on the x-axis. We'll put the left side of the rod at 0, and we'll put the right side of the rod at x equals L. The point charge is a distance A from the rod, so it must sit at a position L plus A. So this distance is A. So we can't calculate the force of the rod on the charge by simply applying Coulomb's law. Because if we did, we would say it's Ke big Q times little q over r squared. But what is r? R is the separation, and you can see from the different parts of the charged rod, there are different separations. So we can't just plug it in to that formula. Another strategy might be to look at the charged rod and say, well, it has total charge Q, say maybe a coulomb, but that's due to a bunch of little excess charges, little excess protons or excess electrons. So we could figure out how far each of those excess charges is from Q, calculate the force, and do the next one and the next one and the next one, assuming they're evenly distributed. The problem with that method is, if this is a coulomb, there would be about 10 to the 26th such forces, and we'd have to add 10 to the 26 terms. So we don't want to do that, even though that's really what's happening. In physics, what we do is treat this as a continuum. So a continuum means we assume that this charge Q is smoothly distributed over the rod. No matter how far you zoom in, you just see smeared out charged. Even if you zoom in smaller than an electron and a proton, you still just think of it as smeared out charge. So the way we characterize that is something called the charge density. So in this case it's lambda. Lambda is the linear charge density, charge per unit length. So lambda, in this case, is Q over L. So when we do these problems, we usually don't worry about Q and L to start, we just call it lambda. Okay? Let's see, so now the way we would calculate the force is to, we have this continuously charged rod, is to think of just a little piece of it, like this. We consider a little piece of the rod and we call it a differential element. So basically here a differential element means it's a piece that's small enough that we can treat it as a point charge. It's a little piece whose size is dx. If it's along the x-axis, its size is the length dx, and just d just means it's really small. It's a little piece of the x-axis. Its charge is dq. If the total charge is q, dq just means a little piece of that total charge. So if we treat this as a point charge, and where does it sit? It sits at some position x, right? It sits at some distance along this axis x. So we can ask ourselves, what is the force? Well, if it's a little differential element, then we must be only getting a differential force. So everything is differential. dF is Coulomb's constant times the product of the two charges. One is dq, and one is q, over r squared r hat, just like before. If we want to get the total charge, then all you have to do is add up all the little dx's, all the little differential elements. Well, adding them up means summing them, and that's what an integral is. We're just going to sum, there's our s, we're going to sum both sides. If we add up the df from each of the differential elements, what do we get? We get the total force. Right? The integral of df is just f. On this side we have to integrate along the rod, so you always want to get all the, everything in here in terms of one variable. In this case in terms of x, right? Because we're trying to integrate along the x-axis. So we want to turn things into x, or if they're constants, we want to take them out of the integral. So Ke is a constant. Right? So that comes out of the integral. Q is a constant. That comes out of the integral. So constant means they don't change as you consider different differential elements along the axis. dq, so let's go ahead and write our integral sign. How do we get dq in terms of dx? dq is just the lambda times the dx. Right? Lambda is the charge per unit length. So we could call this dq lambda dx. R squared, right? So the separation is what? Well, if this is at x, then this distance is L minus x. If the differential element is x, then it's always L minus x from the end. And then this is another distance A. So the separation is L minus x plus a squared. And for this problem, the force of dq on q is always going to be the r hat direction that way. It's always along the x-axis. So r hat in this case is really just the differential, or is just the unit vector I hat in the x direction. So there we've actually put together the integral. We can now take one more constant out, right? This could be keq lambda, and then it's just the integral of dx over the quantity L minus x plus a squared. So let's keep going. F equals keq lambda. Hold the lambda out. Let's go ahead and do the integral. It looks kind of tough, but it's really just 1 over x squared dx, or it's something that looks like x quantity squared dx. So this is not a math class, as I often write in the book, so we'll just do it real quick. We know this is something to the minus 2, so you can bring that up to the minus 1 and divide by that. So that gives you a minus sign. And then you bring that up to the minus 1, so it's minus 1 over L minus x plus a. So we brought it to the minus 1 power instead of minus 2 power. But then we have to divide by the derivative of this thing with respect to x. And what is that? That's minus 1. So those two minuses cancel. So really the integral of that is just 1 over L minus x plus a. But to get a real answer, we have to put limits on the integral. We've been writing this integral without its limits. We don't integrate along the entire x-axis, we just integrate along the part of the rod that really exists. So we integrate from 0 to L. This whole time, this was a definite integral from 0 to L. Okay? So if this is an integral from 0 to L, we evaluate this thing, 0 L. Okay. All right, so let's see. That means that the force is keq lambda. And we plug in L, we get 1 over L minus L plus A, minus L plus A, minus, and then we plug in 0, 1 over L minus 0 plus A. And you can see those two L's cancel. So we have 1 over A minus 1 over L plus A. So if we want to combine those and make it look nice, we just go with the product of the two denominators. So we get them as a common denominator of A times L plus A. So we get this one there, it's L plus A over L plus A. We multiply it by 1. Multiply it by L plus A over L plus A. And this one, to get it to the right, the common denominator, we multiply it by A over A. So in the end we have L plus A minus A is just L. So this thing then finally is equal to keq lambda times L over A times L plus A. We can even go a little bit simpler. If you look at this, you might notice lambda times L is what? Lambda times L is the total charge Q. So let me rewrite that again, and we'll actually make it a little bit simpler. Lambda times L is big Q, so big Q times little q. We could have said like this. Ke big Q times little q over A times L plus A. I hat. And then you can see the answer actually does look like Coulomb's law. It's Ke, the product of the two charges, over some sort of separation, and it's not a single separation squared, it's two separations, A, this end and that end. And of course the I hat, which I forgot to write a few times. And that's the answer. This is a very important fundamental kind of problem, to switch from discrete charges to continuous charges. Very important thing to understand and be able to do.